everyone, welcome to CAIE Physics Possible Walkthrough Series brought to you by ZNotes. I'm Yumna. While I'll be your host, you have an amazing contributor, Rushul, who will be guiding you through all the key concepts and questions for this possible today. Together, make sure you're well prepared and confident for your exams. Don't forget to hit subscribe so you don't miss any episodes. Let's get started and dive into this paper.
Okay, so this one is the summer 2023 paper 4-3, so it's theory. So let's start with it. So question 1 shows a balloon filled with helium gas. The mass of the balloon is 120 kgs. Calculate the weight of the balloon, show your working. Nothing complicated, we know W is equal to mg. So it's just 120 into 9.8, which is rounded off, it's just 1200 Newton. Next, the resultant force on the balloon is 54 newtons. Show that the acceleration of the balloon is 0.45 meter per second square. So we know the formula that force is equal to mass into acceleration. So consequently, acceleration is equal to force by mass. Here, the force is given as 54 Newton by 120 kg. So thus the acceleration is 0.45 meter per second square. C. The balloon accelerates upwards from rest at 0.45 meter per second square for 8 seconds. Calculate the velocity of the balloon after 8 seconds. So we know that its initial velocity is 0. So we have the formula that V is equal to U plus AT. Basically, the initial velocity here is 0. So it's just V is equal to acceleration into time. Since you know that the speed increases 0.45 meter per second each second for 8 seconds. So it's basically just 0.45 into 8, which is 3.6 meter per second. Now, calculate the distance traveled by the balloon in the first 8 seconds. So, for distance traveled, so if we can visualize this like a speed time graph, this whole scenario. So the balloon starts from rest at 0, and after 8 seconds, it reaches a velocity of 3.6 meter per second. So we know that in a speed time graph, the area under the graph is equal to the distance, since distance is equal to speed into time. Hence, the area under the graph of a velocity time graph is the distance. Let me just write V. So here we basically just have to find the area under this graph, which is, as it's a triangle, half into base, which is 8, into height, which is 3.6. So this cancels out. It's just 4 into 3.6, which is 14.4 meters. The other way you can think of this is because there's uniform acceleration from 0 to 3.6, the average speed is 3.6 by 2, which is 1.8, since it's it's 3.6 plus 0 by 2, so the average speed is just 1.8. So we can just do 1.8 into 8 seconds, which is also 14.4 meters. Now, question 2 starts with define pressure. So pressure we know as the force exerted per unit area. Now, describe how pressure in a liquid varies with its depth and with its density. So we know that in a liquid, pressure is equal to H rho G, where rho is the density and H is the depth. So we can clearly see that here it has a direct relationship with both depth and density. So hence for both we can just write uh, increases as it increases. Or a better way would write it will be increases as the depth increases, and same for density. All right, so part B asks us to state two energy resources for which sun is not the main source. So we have three actually, so we can write any two. One is geothermal, which is dependent on the heat of rocks underground below the Earth's surface. That's been there since the Earth was formed, so that's not related to the sun. The other one is tidal. Now, tidal has sun as a source, but it's not the main source because you need both the sun and the moon to, use their gravitational pull to create the tides. Another one you have as a bonus, which you can think of, is nuclear, since that's using nuclear fuel, which is, made of elements present on the Earth. C asks us to state and explain whether each of the following methods of electrical power generation is renewable. Power generation in a nuclear power station. Now, of course, this is not renewable, as we know, because it's a fuel which gets used up. So as we use it, it doesn't automatically get replaced. We have to use up our stores of uranium, etc. Part 2 asks us about wave power. Now, wave power is renewable because, as we know, the waves will automatically get replaced, each second as we use the waves to, produce energy. State which states of matter, this is question 3 now, solid, liquid, or gas, has the greatest thermal expansion and which has the least. So, greatest thermal expansion is obviously gases and least is solids. It's simply because gases have weak intermolecular forces. So, they're just less forces against its motion. So, as temperature increases, as the particles gain kinetic energy, they move faster and thus they spread apart. Whereas for solids, as you know, they're in a rigid structure. Their particles are in a very fixed lattice structure and they can only vibrate around their points. So even as they gain energy, they don't break their structure because of strong attractive forces holding them together. Describe in terms of the motion and arrangement of particles the structures of solids and gases. So solids, as we know, have fixed positions, as we just mentioned, fixed positions in a lattice, and they only vibrate about those fixed positions. The particles don't move around. Whereas gases are arranged randomly, their particles are, and they move at very high speeds because of no presence of intermolecular forces to keep them in place. Now, question B asks us to define specific heat capacity. Specific heat capacity is the amount of energy needed to increase the temperature of 1 kg of a substance by 1 degree Celsius. Or we can write unit mass by unit temperature. Part 2 asks us that a student carries out an experiment to determine the specific heat capacity of a metal. A cylinder of the metal is heated by a 12-watt electrical heater. State the readings that the student takes. So basically, we need to know which quantities are involved in finding out the specific heat capacity. We have the formula that E is equal to MC. One second. Yeah, E is equal to MC delta T, where C is the specific heat capacity. So thus we can write that C is equal to E by M delta T. So we need to know the energy, the mass, and the change in temperature. So we need three readings: the mass of the metal, the initial and final temperature, which will give us the change in temperature. Change in temperature is not a reading we can take. So, we have to take the initial plus final temperature. And so for the energy, so we know that energy is equal to power into time. We already know the power of the heater, which is fixed. So we just need to find out the time, which is the reading we have to take. So that's just time taken. These are your three readings. For A, figure 4.1 is an incomplete ray diagram showing an object O, a converging lens, and the principal axis. The focal points are each labeled F. Complete the ray diagram to draw the image formed by the lens. Label your image I. So as we can see from this ray diagram, the two lines are moving this way, but we can clearly see that they're moving further apart and they're not gonna converge anywhere in this area. So in such a case, we have to go back and retrace these lines as if they were originating from an imaginary point. So we actually have to draw solid lines or dotted lines, whatever you wish. So somewhere around here, these lines would intersect. So this would be the image I formed. Click three descriptions in the list which describe the image formed in I. In one, sorry. So this, we can very clearly see it's larger than the original object, so enlarged. It's upright because it's standing upwards. It's not been inverted if it would have been formed on the right side of the lens. So we can say it's upright, and it's virtual because it's being formed on the same size as the lens, and the lines aren't actually intersecting at this point. They just appear to be intersecting at this point from where they're approaching. So that's why it's virtual. Part B asks us to state the name for the defect of vision that can be corrected by a converging lens. Now, a converging lens. So I'll do these two questions together. That'll help. Basically, a converging lens corrects long-sightedness. It corrects long-sightedness because it basically makes seeing close by objects easier. So that's helpful for those who can't see close by objects easily, and thus they are long-sighted. So part two obviously asks us describe how a converging lens corrects the defect in A. So we'll have to make two not any serious ray diagrams, but just rough sketches. We'll have to draw two like this right now. It's advised you make a serious ray diagram in the exam, though I'm just drawing it here. So as this is the lens in your eye and this is the retina, what happens to long-sighted people is that their lens isn't thick enough to refract the light rays enough for short objects, since they're more suited to objects whose light comes like this. For short objects, the light is diverging hugely. So once it goes through their lens manages to refract it just a bit, but not enough. So they actually end up converging on this some imaginary point behind the retina. So that's why on the retina, the image is a bit fuzzy. Now, what a converging lens in front of the eye does is, so if a short object close by, its rays are diverging. What a converging lens will do is first it'll converge these rays slightly, but just enough so that when the real lens has to converge it, it can do that, forming the image exactly on the retina. Now, how much the light will converge and etc depends on the thickness of the lens, and that's why when you get an eye checkup done, your power is determined to know how much extra refraction you need based on how your lenses are. So yeah, converging lens basically does that extra refraction needed, which can't be done by a natural lens. So we can just say that it refracts light rays from a nearby source. 5A asks us that there's two types of an electromagnetic radiation that's used in glass optical fibers for high-speed broadband. State the type of radiation other than visible light which is used in glass optic fibers. So the other type of radiation is infrared radiation. Then we come to the reasons why it's these two, visible light and infrared, and not any others. So one of the reasons is that even infrared, uh, glass is transparent to both visible light and and some infrared radiation, which means that it doesn't absorb these radiations. So allowing for maximum transport of data, since it won't be absorbed or eliminated by the glass itself. And the second point is that because these carry high amounts of data, and the second reason is that they can carry high amounts of data because they have a higher frequency compared to radio waves or microwaves, and we don't use ultraviolet or gamma rays just because they're too dangerous for regular exposure. Question B asks us that the critical angle of the glass in an optical fiber is 45 degrees. Calculate the refractive index of the glass. So we know that refractive index n is equal to 1 by sine c, or in this case 1 by sine 45, which is 1.41. Part 2 shows us an optical fiber made of glass described in part 1. Draw careful Draw carefully a ray of light in the fiber undergoing total internal reflection. So basically for this one, we need to ensure, since the critical angle is 45 degrees, at whatever point the light is striking the optical fiber, like if you draw perpendicular to that point, the angle of incidence we draw here must be greater than 45. So we can't draw a line like this. We have to draw it like this entering. That's why I'm drawing it far into the optical fiber. So we can draw a ray of light like this. Angle of incidence is obviously more than 45. So hence total internal reflection will occur as it occurs at any angle greater than the critical angle. So then we have to follow the laws of reflection. The angle of reflection will be the same as angle of incidence. So at a similar angle like this, it will be reflected. So yeah, this will just directly go out, or you can make it appear so that it makes one more reflection. But even doing one reflection is fine. So yeah, this will just go out. And as it's sitting here, I'll just draw one more reflection, leading it outwards. So yeah, we it's recommended not to show more than two reflections. Question 6 asks us, it tells us that an electric heater uses a resistance wire of resistance 26 ohms. The power dissipated in the resistance wire is 2500 watts. Calculate the current in the resistance wire. So we know the formula that power is equal to I square R. So in this case, you have to calculate the current, which is I. So I square is equal to P by R. So I is just root of power by resistance. So power is 2500 divided by 26. And when we find the root of the answer, it's 9.81 ampere. Now, the resistance wire of the heater has a length of 1.2 meters and a cross-sectional area of 7.9 into 10 to the power minus 7 meters square. A new heater is designed using wire of the same material with length 1.8 meter and cross-sectional area 5.8 into 10 to the power minus 7 meters square. Calculate the resistance of this wire. So the new wire is what we're expected to find the resistance of. So there's two factors which affects the resistance of like the same material. One is length of wire. Resistance is directly proportional to length. As the length increases, the resistance increases. Not similarly, but another factor is cross-sectional area. Resistance is inversely proportional to cross-sectional area, since the greater the area, the more number of electrons can flow per second, so resistance falls. So it's directly proportional to length, but inversely proportional to area. So the original resistance we know is 26. So now to 26, we have to multiply the factor of like the increase in length, which is 1.8 by 1.2. And then we have to multiply it by 1 by the factor of the change in area. So it's 1 by 5.8 by 7.9 into 10 to the power minus 7. So it's basically the reciprocal of 5.8 by 7.9 to 10 to the power minus 7, which is 7.9 by 5.8, because 10 to the power minus 7 just cancels out. So when we do 26 into 1.8 by 1.2 and into 7.9 by 5.8, we get 53 ohms. So yeah, when you multiply it by the factors of change into 26, you get 53 ohms. C says that the 2500-watt heater is used in a country where electricity costs $0.3 per kilowatt hour. Calculate the cost of using the heater continuously for 2 days. So basically, what's 1 kilowatt hour? Kilowatt hour is basically a unit of energy. So if you're trying to convert it into joules, 1 kilowatt hour is basically, we know that energy is equal to power into time. The energy in joules of 1 kilowatt hour is basically the energy used up when 1000 watt is used up for 1 hour, which is 60 into 60 seconds. So that figure is 3.6 megajoule or 3.6 million joules. So if a 2500 watt heater is used constantly for 2 days, so the amount of energy being used is 2500 into 3600 for 1 hour into 48 hours because 2 days. So it's going to be 2500 into 60 into 60 into 48, which is 432 megajoules. So if we divide it by this value, which is the amount of energy of 1 kilowatt hour, the number of kilowatt hours is 120. So 1 kilowatt hour costs $0.3. So 120 kilowatt hours cost 120 into 0.3, which is 36 dollars. Question 7 says that the voltage across the primary coil of a 100% efficient transformer is 220 and the voltage across the secondary coil is 12 volts. The current in the secondary coil is 2.5 ampere. Calculate the current in the primary coil. So the fact is that the power in a transformer is always constant. The power entering the transformer and the power leaving the transformer is constant, given that it's 100% efficient, which it is here. So power, we know that P is equal to IV, which is current into voltage. So IV is always constant. That means in any transformer question, I1 V1 is equal to I2 V2. So here, 220 volts into X, let's take X as the current in the primary coil, is equal to 12 volts into 2.5 ampere. Hence, by basic algebra, X is equal to 0.14 ampere. Now, part B says calculate the ratio of the number of turns on the primary coil to the number of turns on the secondary coil of the transformer. So this will basically be, we know that the ratio of voltage of primary coil by voltage of secondary coil is the same as the ratio of the number of turns, since the number of turns determines the voltage. The more the turns, more the voltage, because more that's more times the magnetic field is cut, so a greater voltage is induced. So we already have the ratio of primary voltage is to secondary voltage, which is 220 by 12, which is as a result also going to be the same as the ratio of the turns. So 220 by 12 is 18.33. So when we round it to two significant figures, it's just 18:1. During beta decay, one of the neutrons in the nucleus changes. State what happens to this neutron. This is question 8. So we know that during beta decay, a neutron in the nucleus basically splits into a proton and an electron. So we can just write this neutron splits into a proton and an electron. Explain how charge is conserved during this change. So charge is conserved is, so neutrons are neutral, they have zero charge. So here the charge is zero. When they form a proton and a proton is positively charged, so +1. A neutron is negatively charged, so -1. The magnitude of the charges of a proton and electron are equal. So since the proton is +1, electron is -1, the total charge is 1 minus 1, which is still 0. So that's how a neutral neutron gives one positive and one negative. So 1 minus 1 plus 1 minus 1 is equal to 0. So charge, total charge, I think we should say, remains the same. Part B says complete the nuclide equation for the alpha decay of radon 212 to form an isotope of polonium, symbol PO. So you know that alpha decay is basically the decay of one alpha particle, and one alpha particle is basically a helium atom, which has four nucleons, which is neutrons plus protons, and two protons. So basically, we know that from the values of radon, four mass numbers will be subtracted, and the atomic number will be subtracted by 2. So we have symbol of PO 208 by 84 plus, of course, one alpha particle. Now, question 9, figure 9.1 shows the sun as the central dot and the planets Saturn, Jupiter, and Earth labeled SO, JO, and EO. The planets orbit the sun anti-clockwise. From the Earth's orbit, the planets appear aligned. Assume that Saturn takes 30 years to orbit the sun, and that Jupiter takes 12 years to orbit the sun. A. On figure 9.1, mark the positions of Saturn and Jupiter 5 years after the original positions shown. Now, so basically, we know we have the total time period of both Saturn and Jupiter. Saturn is 30 years and Jupiter is 12 years. So here, since we're doing circular motion, we have to work in degrees. So basically, the question tells us that in 30 degrees, Saturn travels 360 degrees, which is one full circle, and Jupiter travels 360 degrees in just 12 years. So now it's asking us to mark both of the positions after 5 years. So if Saturn takes 30 years for, if Saturn for 360 degrees takes 30 years, then in 5 years it's going to travel. So Saturn, 30 years gives us 360 degrees of rotation. So 1 year will give us 360 by 30. 5 years gives us 360 by 30 into 5, which is 60 degrees. So right now I don't have one, but during your exam we have to take out a protractor, taking this as the zero line. From here measure a 60-degree angle, which should be around here, and this is where we mark the position of S1, Saturn. This angle should be 60 degrees. Now we have to do the same thing for Jupiter. So in 12 years, Jupiter moves 360 degrees. So in 1 year, it'll move 360 by 12. Thus in 5 years, it's going to move 360 by 12 into 5, which is 150 degrees. So again, we use our protractor. Starting from here, we measure 150 degrees, which should be around here. So this whole angle should be 150 degrees, and this is the spot J1, this. So now if I clean the diagram a bit, it's basically this is S1 and this is J1. Now, question B says that on the figure, mark the positions of Saturn and Jupiter 20 years after the original positions shown in figure 9.1. So we basically have to do the same thing. For Saturn, it's 20 by 30 into 360, which gives us 240 degrees. And for Jupiter, it's 20 by 12 into 360, which gives us 600 degrees. Now, obviously, you can see that 600 is greater than 360. So what it's trying to say is in this 20-year period, Jupiter will rotate 360 degrees and then again until a total of 600 degrees. So 600 is 240 degrees more than 360. So that means once it's completed its full revolution, it's going to travel 240 degrees more. So basically, you just measure a 240-degree angle, and that's how you draw this one. which should be around this point. You basically measure an angle starting from here, and it should be 240 degrees. So, which is around this point. And for Saturn, it's, since it's less than 360, it's nothing complicated. And this is S2, which is also 240 degrees by coincidence. Well, not coincidence, that's what the next question is about. State what is observed from the Earth's orbit after 20 years. Basically, since they've rotated the same degrees, they appear in the same line from the Earth's orbit. It doesn't here because, of course, this is a rough drawing, but when you actually measure the angles, it will. Now it does. So we just write that the two planets appear linear. Yeah, in the same line. Question C asks us to choose two words from the list to describe each planet. So we know that the first four planets of our solar system, we have 8 planets. The first four are smaller than the last four planets. Earth comes in the first four, Jupiter comes in the last four. So Jupiter is large. And we know that Jupiter is much larger than the Earth. Jupiter is large, Earth is small. And we also know that the first four planets are rocky planets. That's why it's the ground is solid where we live at the Earth. But the other four are gaseous planets. You can see the way they look on the internet and stuff. Jupiter, Saturn, they're made of clouds of gas. So the Earth is the rocky planet, whereas Jupiter is a gaseous planet. Now, the next following part asks us that the average density of Jupiter is much less than that of the Earth. The gravitational field strength at the surface of Jupiter is greater than that at the surface of the Earth. Explain how these differences in density and gravitational field strength are consistent with your answers to C part 1. So, density, as we mentioned in part 1, Jupiter is a gaseous planet and Earth is a rocky planet. So Earth is solid, Jupiter is gaseous. So since Jupiter is gaseous, it's less dense than Earth because the Earth is solid. Since obviously in the gas particles are spread apart, whereas in the solid they're close together in their lattice structures. Gravitational field strength. Now, this will require two things to be mentioned. So the gravitational field strength at the surface of Jupiter is greater than that at the surface of the Earth. This is because the mass of Jupiter is greater than the mass of Earth. But now the point being that if Jupiter is less dense than Earth, how is Jupiter heavier than the Earth? So we know that mass is equal to density into volume. So basically what we have to explain is that though the density of Jupiter is less than Earth, the volume is greater than Earth by a greater amount than the Earth's density is greater than Jupiter's density. So, for example, just a rough example, if the density of Earth was 10 more than Jupiter, these are just roughly, it's just an example. The volume of Jupiter is 20 more than Earth's volume. So, basically, what you have to write is the volume of Jupiter, or we should say in the amount by which the volume of Jupiter is greater than the volume of Earth exceeds the amount by which the density of Earth is greater than the density of Jupiter. So basically, the volume change offsets the density difference, which is why the mass of Jupiter is greater than the mass of Earth, which gives a greater gravitational field strength. So the average density of Jupiter is 1300 kg per meter cube, and its volume is 1.4 into 10 to the power 15 kilometer cube. That explains the previous question. Calculate the mass of Jupiter. So as I just mentioned, mass is equal to density into volume. Density is 1300, whereas the volume is not exactly this. Since we have meter cube in density, we have to convert this to meter cube, for which we have to multiply this value by 1,000 three times, since it's meter cube. So 1.4 into 10 to the power 15 into 1,000 uh, three times, which gives us 1.4 into 10 to the power 24, which is, the answer is 1.82 into 10 to the power 27 kgs. That's the mass of Jupiter. So yeah, we basically changed the units, brought it into meter cube, since this was kg per meter cube, and we got 1.82 into 10 to the power 27. Question 10a asks us to show that 1 light year is equal to 9.5 into 10 to the power 15 meter. So light year, while many people get confused, is a unit of distance, not time or anything. So it's basically the amount of distance light can travel in 1 year. So we know that distance is equal to speed into time. So the speed of light, we all know, is 3 into 10 to the power 8 meter per second into the time, which, so we're basically calculating the time of 1 year in seconds, which is 60 seconds per minute, into 60 seconds into 60 minutes per hour, into 24 hours per day, into 365.25 days in a year. So these many seconds are in a year into the speed of light, which gives us, it gives us 9.47 into 10 to the power 15 meters, which rounded off to two significant figures is 9.5 into 10 to the power 15 meters. Question B1 asks us to state one measurement that is taken when determining the speed v at which a galaxy is moving away from the Earth. So one measurement we take is the amount of redshift, or we can also write that as the change in wavelength, because as we know about the Doppler effect, so the Doppler effect is basically, if you've observed in nature, so let's say this is a police car with a siren which is playing a sound, and you're a car, you're stationary, or you're just a human, you're standing. The police car is moving away from you. So let's say it generates one wave here, and its wavelength normally is about this much. But then by the time it's generated the next wave, the car moves here. So the next wave generated here. And by the time it's generated the next wave, the car is moved here. And by the time the waves have moved here, so you eventually start to see the wave being stretched out. So it appears like this. Because while this much was the distance that should have been maintained, the car keeps moving away. So the source of the waves keeps moving away. So that's why the distance between the waves keeps increasing, because those waves keep moving backwards and the car keeps moving forwards, so wavelength increases. This is basically the Doppler effect, and it's basically what happens with these galaxies. So here's our Earth. These galaxies keep moving away from us. So again, the wavelength of the waves they transmit keep changes, since they keep moving away from us. It's this much, then keeps increasing. So that's how we can calculate how far the galaxies are moving away from us, by calculating the amount of redshift, which when we plot the wavelengths on uh, paper, we can see the black lines in the color spectrum, and we can see that the lines keep shifting towards the red section of the spectrum, because infrared light has a greater wavelength. Red light has a greater wavelength, so we can see the waves being stretched out and the wavelength increasing. That's why amount of redshift is used to determine how fast a galaxy is moving away from us, because the faster, the greater the wavelength, the greater the redshift. Part 2 asks us to write down an equation relating v and the distance d of a far galaxy. We know that this is exactly what the Hubble's constant is about. So Hubble's constant is 0 is equal to v by d. Hubble's constant is basically a constant used. It measures the ratio of the speed by which galaxies move away from us by the distance they are away from us, which obviously they're directly proportional, since the faster they're moving away from us, the further away they are from us. Part 3 asks us to state how the distance of a far galaxy can be determined other than by using the equation in part 2. So, a second way to determine how far a galaxy is to calculate the or to measure the brightness of a supernova in that galaxy. So basically, supernovas have a general same brightness. So we can see that basically what a supernova is caused when a red supergiant basically runs out of elements to use for nuclear fusion, runs out of energy. So it explodes one last time as a supernova. So this explosion generates a lot of light, since it lets go of all that energy as light. And so of course the farther away something is, when it erupts light or erupts in the form of light, the brighter we'll see it, the closer it is. So the further it is, we'll see it less brightly. So since the brightness of a supernova is generally fixed, the brighter it appears to us on Earth means the closer it is to us. So that's why the brightness of a supernova can be used to find out how far the galaxy is, since a further if a galaxy is very far away, its supernova won't appear very bright. So that's how. So yeah, that's question 10 over, and yeah, that's it for today. This paper is over, so we've ended summer 2023.
Okay. That wraps up today's episode. We hope you found it helpful and feel more confident about tackling past papers. We've got plenty more episodes coming your way, so don't forget to subscribe and hit the notification bell to stay updated. Thanks for watching, and we'll see you next episode.